Hello everyone. In this lesson we're going to take a look at chemical reactions. Now we know what chemical bonds are. We know they're an attraction that exists between atoms and they form because atoms are trying to reach a stable configuration. Well, in a chemical reaction those bonds are going to change. We're going to make new bonds and break old bonds. So a chemical reaction is actually the process of breaking bonds and reactants. Now reactants are the things that react, that's what we start with, and then we reform things to make new products. Those are the things that are produced in a reaction. Remember, bonds can be ionic or covalent. Ionic bonds form when electrons are transferred between elements, and covalent bonds form when two atoms share valence electrons. Reactants are what we start with. They react. That's why they're called reactants. Products are what we end with. That's what's produced in the reaction. That is why they're called products. And then valence electrons are involved in the chemical reactions because old bonds have to break and new bonds have to form. Now, during a reaction, we have what's called the law of conservation of mass. It's just like all our other conservation laws. It means that this stuff stays the same. Conservation of energy, the amount of energy stays the same. Conservation of mass, the amount of mass stays the same. So that means atoms cannot be created or destroyed in a regular chemical reaction. They only change how they're bonded. So whatever mass we start with is also however much mass we end with. Now, this leads to some interesting things where we have to do what's called balancing some reactions. For now, we're not going to get really into that, but let's take a look at what's going on here. This is an equation for a chemical reaction. It shows us that we start with hydrogen gas, and it reacts with oxygen gas to produce water, H2O. Now, why are these twos out front? Well, if we start with hydrogen, hydrogen is H2, which is two hydrogen atoms bonded together, and it reacts with O2. Oxygen is two oxygen atoms bonded together. They're bigger because oxygen is a bigger atom. Now, the first thing that has to happen for this reaction to occur is actually for these things to break apart. So if I have hydrogen, these two hydrogens are going to separate. So they come here. And these two oxygen atoms are going to separate. And so they split apart and we get an oxygen atom and an oxygen atom. Now what happens is these things form new bonds. So they used to be bonded to themselves. Now this hydrogen can come over here and hang with that oxygen, and this hydrogen can, okay, so we get our hydrogen atom, our big oxygen atom, and our little hydrogen atom, and that's water. But you'll notice we still have one oxygen atom left over. Well, we can't just get rid of it, and the reaction doesn't say plus O, so where is it at? Well, that's why there's twice as much hydrogen as oxygen, because really there's two sets of these things, right? So we had our two hydrogen molecules, and they're going to split, and now this guy can come and bond here, and this guy can also come and bond here. So we actually get out of this is two molecules of water. That's how mass is conserved. So there's 1, 2, 3, 4 hydrogens, and we started with 2 times 2 is 4 hydrogens. And then we have 2 oxygens as well, and so the amount of hydrogen and oxygen didn't change, but we started with hydrogen atoms, and we started with oxygen atoms, and then we end with hydrogen bonded to oxygen, and we get water. So we get a new thing. A similar thing could happen with an ionic bond. So you have iron, it'll form four iron atoms will donate electrons to 6 oxygen atoms, and then the resulting ions will stick together and we'll get 2 formula units, or crystals I guess you could consider it, of iron oxide. This would be rust. Again, that's 4 irons, 2 times 2 is 4 irons, 3 times 2 is 6 oxygens, 2 times 3 is 6 oxygens. So if you count it out, there's 4 of these, and 4 of them over here, 6 of these, and 6 of them over here. The amount of matter did not change, just how it was bonded together. Now, a chemical reaction is very different than a physical change. We've looked at physical changes before when we looked at phase changes or matter's changing state. That's because we start with water and it boils, so we end with vaporized water. We didn't change what we had. If you take a board and cut it in half, you have 2 shorter boards, but they're still boards. So you still have the same thing you ended with as you began with. In a chemical reaction, that's going to change. Chemical reactions change matter into new stuff. Iron rusts, and when iron rusts, we get rust. It's not iron anymore. It's crumbly and reddish and doesn't have very much strength, and it's ionic. It's a different thing altogether. When we take hydrogen and we react it with oxygen, we end up with water. It's not hydrogen, it's not oxygen, it's water. We have different things than we started with. So in lab, you guys looked at a few different compounds that reacted, and you could visually see if a reaction had occurred. Generally you can, but it's not always the case. There's a couple different signs you should look for. Now, not all of these guarantee a reaction is happening, but if you do see them, it's a pretty good indicator that you might have a reaction and you should do a little bit more investigating. So one of the things you'll see is new things that didn't exist before. So if you get something new that wasn't present before, yeah, you had a chemical reaction. And one of those things that is hard for us to see is gas forming, but not boiling. So we kind of, if you've ever done the baking soda and vinegar thing for a volcano, you've seen gas bubbles form from a chemical reaction. Those gas bubbles are new things. We didn't have gas before, and it's not because that vinegar started boiling, it's because it reacted with baking soda and formed carbon dioxide. If you have a temperature increase or decrease, you pour a couple solutions together and it gets hot or it gets cold, that could be a chemical reaction. It isn't always, but it is a good indicator of that. If this color of something changes when you mix solutions together or bubble some gases through something, you get a color change, that's a pretty good indicator of a chemical reaction. If you've ever watched iron rust, it changes to reddish. If you've seen the green patina that shows up on copper, that's a chemical change. If you've just heated up metal until it's glowing orange, that's not. You just made hot metal. If you get the formation of a precipitate, and we saw this in lab, when you mix two solutions together, you got that white cloudy substance, that was a solid. So a precipitate is a solid substance that forms when liquids come together. And in fact, when milk gets all chunky, when it gets all spoiled and rotten, that is actually a chemical change. It's forming a precipitate. Now, because a chemical reaction involves breaking old bonds and forming new bonds, we know we need atoms to collide with enough energy to actually break those old bonds. So we can speed up chemical reactions by making the collisions happen more often. So basically, we can make the reaction happen quicker. We're going to either need to find a way to get more collisions to occur or reduce the amount of energy that needs to be there for the reaction to occur. So the ways we speed up a reaction, we increase the temperature, which makes things move faster. And if they move faster, they're going to collide more often and collide with more energy. And that's going to mean it's more likely that old bonds can break and new bonds can form. We can put more stuff in there, that is to say increase concentration, because if there's more stuff, they'll hit each other more often, and that means more collisions. We can increase surface area. Basically, we would rather have lots of little pieces rather than one big chunk. And that's because if I have one big chunk, all we can get to are the edges on the outside, right? A reaction can happen on this edge, and a reaction can happen on this edge, and a reaction can happen here, but we can't get into the inside of it. That's blocked off. But if I take that thing and I cut it up into lots of little pieces, then all those little pieces have lots of little edges, and all those little edges are exposed, and so that means there's more and more and more places for that reaction to actually occur, and so the reaction happens faster when you have more surface area, because before we could only get to the outside, but now we can get to the inside as well. So we've exposed more places for more collisions to speed up the reaction. Stirring will also speed up a reaction for exactly why you think it would. It's going to add some energy. It's going to make those particles move faster. They're going to collide more often. And then there's a trick we can do to lower the amount of energy it takes for a reaction to occur. And that means we're going to add a catalyst, which is basically something we put into the reaction that holds those particles together so that they can form bonds, but it doesn't actually change what product we have, and it doesn't get consumed or changed in the reaction. So the catalyst that speeds up the reaction without changing the reaction. And we could also put something in there that would slow the reaction down. It's called an inhibitor, and it's going to prevent those things from colliding with each other, and so the reaction is going to happen slower. Chemical reactions, we do hundreds of them every day. Our body is carrying out lots of chemical reactions. Plants carry out chemical reactions. Chemical engineers are designing new chemical reactions. Why do we care about these things? Well, one, because we're alive. Photosynthesis is a chemical reaction that converts light energy into chemical energy, and then we can get that chemical energy out through chemical reactions in the process of cell respiration. If you drive cars or use electronics, those things are powered by fuels, whether it's electric energy, or gasoline. We have to be able to do chemical reactions to make those things and get the energy out of them. And then all the materials that we use, from plastics to glass to the batteries in them, soaps, These are all things that have been designed by chemical engineers, and lots of chemical reactions go into making them. And maybe the big one is pharmacology. There are new medicines being developed to fight diseases and help us lead longer, healthier lives. It is chemical reactions that allow those things to be developed.